Happy to see so many people here. I wasn't really expecting that, but this is great. So this talk will be about Spegel, which is a stateless cluster local OCI registry mirror. It's a mouthful, but hopefully by the end of this presentation, things will make a bit more sense. So who am I? Just quickly, my name is Laine. I live here, so had a pretty easy commute. Swedish-Finnish. I'm the creator of Spegel. Created a company around that called Reflektion. I used to be a maintainer of Flux CD, which is like a continuous delivery tool for Kubernetes. You might also know me for writing my opinions about open source. So just quickly, some recap, some introduction about where we are today in the state of like OCI registries and running clusters in production. So we've kind of solved the bigger challenges of scaling containers, right? Kubernetes is generally seen as like a standardized tool for how to run containers. But the challenge that we haven't really looked at as much is how to actually distribute these binaries that then run these containers. So in reality, it doesn't really matter if you can scale to tens of thousands of nodes if you can't actually distribute those binaries, right? So especially if we're running something and then we have to scale to like deal with the additional traffic or whatever we're getting, and if the OCI registry is down, tough luck. So generally, what we look at is like three things when it comes to distributing images. It's availability, speed, and cost. I think you would tend to either prioritize one or the other. You're either spending a lot of money to get speed, or you're reducing speed because you need to deal with fault tolerances and stuff like that. So out in the wild, we see these things as rate limits. So a typical problem I think most of you have experienced is like rate limiting from Docker Hub. The K8s registry even has like some weird IP blocking, especially if you're running like Hertz or Cloud for some weird reason. But this is like a typical problem even now with like the new paid subscriptions for Docker Hub. You can be rate limited even if you're scaling too quickly or if you're spinning up very large new clusters. We've also seen outages. I don't think I want to call out any specific registry, but this is like something that we see with all registries out there. I think a bit more common is like the public, especially free ones, like Docker Hub and GitHub Container Registries has had like a couple of outages. I think GitHub Container Registries was down like 2 weeks ago or something like that for a few hours. But also, a lot of public registries tend to limit bandwidth. I think Docker Hub does like 100 megabits a second or something like that, and that's what it caps you out, at least for non-authenticated users. And then we also see like image removals. This was highlighted recently if it was KubeSphere that took their private registry or whole repo private and removed all the images from GitHub Container Registries. And there was like a lot of the community was looking at this and going like, oh God, what are we doing? I can't scale, like the images aren't available. Like these are things that we see out in the wild today that are like consistently a problem. It's not like was a problem, it's like still a problem, and we seem to not really look for solutions for these things. So our options generally is to, no matter the solution, is to try to take these artifacts and move them closer to us, right? It's either by running some sort of private registry type, like kind of close to your clusters. So it's probably within your own private network or your VPC or whatever it is, and you're investing a lot of time in maintaining and managing, like defining either what images are supposed to be copied over and then paying for the storage to actually keep them there. Or you're doing some sort of like smart pull-through caching and looking at like how many times an image is pulled and therefore like scoring the images based on like that. But really, these solutions move the problem closer to you, right? You're saying, okay, great, this public registry isn't good enough for me or this private registry, if it's ACR or ECR, let's shift the burden on top, like to the operations side. But you're still having this issue of, well, what if this registry goes down, right? So you're kind of just shifting it. Great. So before we move forward, just like how many people have read the OCI spec, like the image spec or the distribution spec? A few. Okay, great. For the rest of you, this is going to be just some foundational knowledge, because I realize that every time I talk about this without giving this like slight introduction, like it becomes very hard to understand. This is the image spec, basically in one diagram. So when we talk about like OCI images, what we actually mean are loosely coupled JSON files referencing arbitrary binaries. So basically, you have in a multi-architecture image, you would have an index. This index has a SHA-SUM. The SHA-SUM of the index is just the SHA-SUM of the contents of the file. It, in turn, references a manifest by the SHA-SUM. So you have to think of it as technically you're walking backwards. So to create the index, you would need the layer. The layer would have a SHA-SUM in itself. The manifest references the SHA-SUM of the layer. Basically, we're creating what's called a Merkle tree. So there's some like self-verifying aspect of this too. So you're not able to modify the contents of any of the downstream components without modifying the upstream SHA-SUMs, right? So when you, for example, when you deploy and reference an image based on the SHA-SUM, what you're actually referencing most of the time is the SHA-SUM of the index, right? So just to visualize this a bit, this is a website called oci.dag.dev. It's created by John Johnson, I think, at Chingard. It's really good because it like helps you like actually like explore the components of an image. So this is the actual image for Spegel. You can see here, this is the index file. It has a list of manifests for different architectures. So this is like the Linux AMD 64 one. This is the SHA-SUM, the reference. We can click there, and we can see here that this is like the manifest. It has the layers, like the actual binary data that composes the actual application, the application that you can run. And then it has a config reference. The image config is mostly information for whatever OCI runtime to actually explain how you run the binary, right? So in its base components, really, OCI is JSON files that reference each other. It's really not that complicated. The distribution spec defines how we actually distribute these artifacts. When you pull an image, it's not actually like you're fetching the whole binary or the whole blob at once. You're actually fetching multiple components. So to fetch the manifest, you're making individual HTTP requests with just the name of the repo and then the reference. The reference in this case could be technically a tag, but also a digest. And then it just returns the JSON file back. The same thing with the layers. It's just a different endpoint with blobs. And you give it a digest, and it just feeds you back whatever is on that digest. So this is like the most basic implementation of an OCI registry that you can implement that is read-only. Technically, the distribution spec also allows you to only implement a read-only registry. The pushing part is a lot more complicated because there's a lot of like, what happens if the push or the upload of a blob fails halfway through, and like how do you retry these things? But yeah, that's like a whole different story. So the challenge, where we are kind of today if you're not using Spegel, or where I was. So back 5 years ago, I was running Kubernetes clusters for some larger customers in Sweden. We had a lot of issues with container registries either going down, but also hitting pull timeouts on Docker, where basically ACR wasn't serving the layers fast enough. At the time, the customer really didn't want to pay for us to manage and maintain these like registry mirrors. So we're kind of stuck in between the situation of like, great, we're going to have downtime, and they're not going to be happy about that, but also we can't spend time creating these registries, right? Around that time, I attended a talk at a meetup, and there was this guy, I forget what company he worked for, but he was talking about his like 1 a.m. Issues when Docker Hub went down. And he was explaining his solution that he wasn't really proud of, but it was just like kind of like what you end up doing if like you can't scale because Docker Hub's down. You can't just go like, oh, I'm going to go back to bed, right? So what he ended up doing was SSH SSHing into the nodes, running Docker export, getting the tar, SCPing it onto the next node as it scales up, SSHing into that node, and then Docker import, right? And he was just doing that as like new nodes were coming up. He was just like SCPing these tar files back and forth. It works. It's not great. You're kind of like a mechanical Turk, right? But it works. But this made me start to think, right? He's doing this. He's up at 1 a.m. and he's doing this manually. But all the commands he's running could be automated, right? It's not like it's anything special with these like CLI commands. And apparently all the data is there. So if it works for him, why can't we automate this? So there's a few like open questions that came to mind around that time, and that's like, first of all, how are images stored? At that time, I wasn't really familiar with like the OCI spec, the runtime, and like containerd and all these things. So it was like mostly me thinking about like, okay, how are registries actually implemented? How are the images stored when a container runs? And then also like looking at like, well, how are existing register mirrors implemented? And then the fourth component there, which is like slightly outside of OCI, which is like discovery, right? Every node in a cluster doesn't run every single image. So how do we discover other nodes in your large cluster that has the image that you're actually looking for? So what I spent a lot of time thinking about this. Mostly I didn't have time to implement it, but it was just something that was in the back of my head, and I kind of like had this feeling that like, oh, there has to be somebody else who implemented this, right? And I was Googling around. I found some alternatives. Kraken, I guess, is like the most was at the time the most popular one, but in my head, I'm like, from my perspective, I'm kind of lazy, you know, like I don't like running stateful applications. I don't like managing them, mostly because it's like it requires some human input or putting some thought into when you do upgrades or when you try to shift clusters. So in my head, I was like, okay, great. There has to be a simple stateless solution. So about now 3.5 years ago, I sat down in between like Christmas and New Year's to start sketching on a new solution. And what I came up with was Spegel. So what Spegel does from this great GIF that a friend of mine created is it enables Kubernetes nodes to pull images from each other. It's in its simplistic form. But when you start looking at like the details of it, Spegel is completely stateless. So, and that's one of those things with like the stateless OCI registry is one of those things that people just go like, that doesn't make sense, right? There has to be state somewhere. There is, but we'll get into it. But yeah, in its basics, what happens is a Kubernetes node, when it starts running try to run a container, it will look and see if this container is cached locally on the node. If it's not, it looks if it's in the cluster. If it's not, it falls back to going to the upstream registry, right? That's the basics of it. So just to give some numbers, because everybody loves numbers, when you serve images from within your cluster, you see around a 80% performance in image pull speeds. These numbers seem kind of crazy, but that's kind of where a lot of the end users are reporting and what my benchmarking is running. So I've created also a benchmarking tool. You can read it in the docs because there really isn't a good one out there right now that spins up a bunch of pre-made test OCI images of known layer size and layer quantity. So you're able to like spin up a bunch of pods and then measure basically the startup time for each pod, basically, and then it makes it into a nice graph. So you can actually run this benchmarking tool and compare it with your existing solution, and then run Spegel on top of that and see kind of like how things compare. So image storage. One interesting aspect of containerd. So Spegel currently only works with Containerd. There has been attempts. I've made some attempts to implement support for cryo. It doesn't really work. There are specific details for this. But one interesting aspect and what enables Spegel to actually work properly and be stateless is that when you look into Containerd and how it works, you realize that it actually stores the images that you run on disk on the host. So it's kind of cool, like, and that's why Docker export works, right? So if you run Docker run, it pulls the image, and then you can run like Docker export and actually get the image back. And that's like kind of the thing that I was thinking about when I saw this presentation of basically SAPing the tar files basically in between nodes. So what Containerd does is, by default, if you don't change any settings, when it pulls an image, it stores these layers in varlib Containerd in this path. The layers files are the SHA-SUMs, so they're really easy to find, right? What another aspect of it is, at least in Kubernetes, this isn't always true in all other scenarios. Containerd has some implementations. It implements some sort of like garbage collection. So it like what you can basically set on like a kubelet level is basically like when disk pressure increases up to like 80%, it communicates with Containerd and goes like start like deleting images so that we don't overflow the disk. And what Containerd does then, it has like its own like a ranking algorithm to like figure out like, first of all, like let's not delete images of running containers. That would be kind of stupid. But also then like look at like what are the images that are least used and stuff like that. But yeah, so what you can basically do is even images for containers that aren't running anymore will persist on disk, right? And if you consider also like how the relationship between like how pod scale and node scale in relation to the persistent of images, you realize that generally, especially if you're running multiple replicas of something, you will always have a situation where the image will exist on one node, right? So you can start to think of like how Spegel works in the sense of like where you can avoid downtime by basically relying on the fact that, well, as long as a container is running with an image, it will be somewhere else. So even if the upstream registry goes down, you're able to spin up a new pod and then pull the image from the existing node that already is running that pod. So especially if you're doing things like draining nodes. So you're trying to coordinate and drain a node, and then you want to, like, because it's old or whatever it is, if it has an issue. If you have like pod disruption budget set up properly, what will happen is the new container will spin up, pull the image from the existing node, and then start up. And once the new container is started up, that's when the old node disappears. So you end up in a situation where the image really never disappears from the cluster at all, right? This work would not be possible without the great folks at P2P. Is anybody familiar with libp2p? No? Oh, one person. Yeah, it's a great project. Basically, it is an attempt to create standardized peer-to-peer libraries for multiple languages. So there's like a library for Rust, JavaScript, Go, of course. I think there's a Java one too. Most of these libraries are used in projects like IPFS, but also I think Filecoin is also one of the main contributors there. They do a lot of critical work in the tools that I use basically in Spegel. So the main challenge that you kind of face when you try to implement something like Spegel is, great, I have this cluster of nodes, right? There are images, or technically layers of a specific image that are cached on disk, but I might have thousands of nodes in my cluster. How do I know when I want to pull an image from within my cluster where I'm going to pull from? So some might answer, well, Kubernetes exposes images in the node status. That is true, but there is a caveat to it. By default, it only exposes the 50 oldest images. You can technically increase this, but it's mostly a limit set to protect etcd. So if you consider the fact that you have like hundreds of images on thousands of nodes, you're basically going to be filling etcd with just a bunch of information about your images, right? So you can't use the Kubernetes API to discover this. I spent a lot of time trying to come up with something stateless. I looked at different types of like distributed key value stores. I initially implement this with Postgres. Not that great. Not that Postgres isn't great. It's just that it's not like the best solution for this type of problem. Is there anybody out there that kind of like sees like what type of problem we're actually trying to solve? Because it becomes like so simple once you realize, and then it took me a while, sadly, for me to realize what problem I was solving. Basically, it's a bunch of computers have files that they want to advertise, and other computers want these files. It's BitTorrent. It's literally BitTorrent. So when you figure out that, oh, it's BitTorrent, you go look at Wikipedia and go, what does BitTorrent use to discover files? Turns out they use a distributed hash table in a specific implementation called Kademlia. So what's cool with Kademlia is that it's basically based on a white paper published like back in like 2001. But basically, it is a distributed hash table that does XOR distancing. You can read it. I still don't understand the maths completely, but what is cool with Kademlia is it actually scales to tens of thousands of nodes. So what basically happens is you advertise out to this distributed cluster of nodes to go like, these are the layers that I have. And the other component of Kademlia we can do, or the distributed hash tables you can look up. So you can basically go, which nodes can you find in this like distributed hash table that have advertised to this specific SHA-sum? And the lookup time generally is around like 2 milliseconds, 1 millisecond. So like it really scales, which is like pretty cool. Plus it's stateless, which is the other aspect of it. So just to like give some better visualization of how Spegel works, Spegel runs, as you saw in the GIF, on each node. So it runs as a daemon set where each node runs a read-only registry that is bound to localhost on the node. It then writes to containerd's mirror configuration to basically go, first you try me. So it basically writes a mirror entry that goes localhost, and I think it's like 30200 port or something like that. I forget what port it is. I should probably remember that. So when containerd wants to pull an image, what happens is it hits localhost first. So it hits the local registry. And the nice thing with containerd is if all the mirrors fail and it has like an order of mirrors that it goes through, it just falls back to the upstream registry, right? So when Spegel gets a request for example, a SHA-sum, it goes and it uses Kademlia, or the distributed hash table, to look up in the cluster of like who has this layer, and then it just does like a HTTP proxy forward thing. So it's really simple, really. It's just like a registry. It has a distributed hash table, and it proxies the requests. And then on the other end, you have whatever instance of Spegel in your cluster that receives this request, reads directly from the host, from that var lib containerd blobs, and just serves that layer directly from the host disk. What's nice about this is actually that, especially if you're running high performance compute, or generally most people today, most OS host disks in most cloud providers, and even like on-prem, are high-speed NVMEs or SSDs, right? We are long gone or past the part of like running on like hard drives. So generally it's pretty quick to serve like data from disk. Mostly because it's like write speed is important for like container logs. We have to like write them to disk, but also like it's important when you're actually pulling images that the disk that you're writing to is actually fast enough, because otherwise that becomes the bottleneck. So this is like the basic architecture of Spegel. It's literally like just 3 components. It's a HTTP server, it is an integration with containerd, and then it is some mirror configuration magic that happens. Yes, perfect. This is the slide I wanted. So Spegel is actually, for a lot of people, a fire and forget kind of solution. So my biggest problem with Spegel today is that people go, I have installed it. Great. Does it work? because it's a best effort cache that mirrors images, it's actually very hard to build a solution that goes, yeah, I totally know that it works or not, because it's like, well, if it's serving the images, well, then kind of, yeah, it should work. But this is just like a cutout of like different Kubernetes providers. AKS works out of the box. Spegel is actually integrated. It's embedded into both K3s and RK2, so you can just like use it as a feature there, and it's pretty cool. EKS requires some configuration. GKE does not work currently because they do some specific containerd configuration. If anybody works at Google here, no, it's something that hopefully will be fixed in the future. But yeah, for the most part, it's one of those things because it's stateless and it requires little input, and because if anything goes wrong, it falls back to the upstream registry. You tend to not see how it's working in the background. The only thing you really experience is increase in speed. So as we talked about, like around 80% improvement in like in pull speed, and hopefully you sometimes see a reduction in your network billing costs, which is like one interesting aspect that I really didn't consider when I initially developed Spegel. Growing pains, yeah. So unexpected use cases. So I built Spegel to fix my issues for in Sweden, large Kubernetes clusters in the real world, I guess, outside of Sweden, we would not be considered large. But it was something I built really to solve our specific use cases. And since then, it's kind of taken off. So adoption has grown quite a lot. And I've heard from a lot of people explaining, like telling me about their solutions and their use cases. So initially, I think a lot of the adoption came from home labbers, really hitting the issues of like, oh, Docker Hub rate limiting, and I don't want to maybe pay because I'm a small end user, and like this is, yeah, I don't want to spend my own money on this. And that was fine. It was people, friends of mine, running at different companies, running like best effort caches that they thought were like good solutions. And then larger companies started reaching out because they found really good use cases in distributing AI models. So as like the whole AI boom has happened, think of it, have your own opinion about if it's good or not. But the reality is these images tend to be large. I think Llama, the OCI image there is like 70 gigabytes or something like that. So if you're pulling this, especially from like public registries, first of all, you're egressing to the internet to pull these images. So you're limited in the bandwidth that you're getting there. But also you're paying that network cost, right? And especially if you're running multiple replicas of these containers, you're pulling 70 gigabytes each time you want to scale, right? So over time, the amount of data that you're actually like pulling in like accumulates. So because you're hitting around in a best case scenario around a 70%, 75% around like cache hit rate on Spegel, mostly because you're like pulling images. That also then results in a 75% network cost reduction, just related to the image cost and distribution of it. Yeah. So the people I've talked to, like, I get a lot of questions about like, does it scale? Does it actually work? It's around like 1,000 plus nodes, 2,000 nodes is what I've heard is like what people, the largest people running Spegel currently run it at, and around like 100 gigabytes of like image sizes is like kind of the max. There are some issues related to this, which I will talk about now. Leader election. People familiar with how Kubernetes leader election works? It's kind of like, so a typical scenario is you're running a controller and you want to elect a leader that is responsible for reconciling a resource, right? So in Kubernetes, there is this concept in the API server that like exposes leader election. So basically getting leases on a resource that basically selects one controller and it's thread safe. I'm doing a really poor job explaining this. But turns out that like leader election and the way it's implemented in the API server, wasn't really designed for running 1,000 pods doing this at the same time. So typically when you run leader election is like your ingress controller or something doing leader election and you have like 3 replicas, right? That's fine. Because Spegel runs as a daemon set and you have 1,000 nodes, you're going to have 1,000 pods. So what I was running leader election for was to bootstrap the distributed hash table. So the challenge when you're running a distributed hash table is you need like a leader node that everybody connects to first so that they then find each other. Because if everybody connects to random nodes, you get what is like a split distributed hash table. So you want to basically have some sort of like known way of everybody agreeing on a set of nodes that they connect to. So what I was using initially was leader election. Turned out that if you do this with 1,000 pods, Spegel ended up using around 50% of the CPU usage from an API server. Probably not the best solution. So this was one of the first times like I started realizing that people were running it at scale, and also like we needed a better solution. So currently I switched over to doing a DNS-based solution. So it just does a DNS, like a round-robin DNS lookup, and then it sorts IPs and then selects the 5 first ones. And this way, every node chooses hopefully the same 5 nodes. But even if like the IPs differed a bit, you'd get some overlap, and it runs continuously also. So it like keeps like refreshing its routing table. So if you ever think about running leader election with 1,000 pods, you probably should. Another issue is thundering herd. So a typical problem is you have a single node that has an image, and then you scale 100 new replicas, and there's only one node that has this image. You end up in a situation where all your nodes in your cluster just going like shouting at this single node, and you're basically gonna consume all the bandwidth. This is a problem that I'm seeing today with some users. Basically, especially large images. Because currently Spegel doesn't have any type of rate limiting, so you're basically going to end up in a situation where a single node is just going to like crumble apart as it's trying to serve like hundreds of gigabytes of data to like thousands of nodes. It's something that I really didn't consider, mostly because when I was working with Kubernetes with customers, I wasn't at this scale. I wished I was at this scale. I'd build stuff because I thought I would ever be at that scale, but yeah. So this is something that is like a critical problem with Spegel today that I'm currently working on, but really something that is not that easy to imagine in a distributed system until you actually see it in real life. So features, some things that I'm excited about. I'm like very much in like reading what's coming next in like the OCI specs and stuff like that. Probably not something that's interesting to talk about at the dinner table, but yeah. So OCI volumes, I guess a lot of people have at least seen the changes that have been coming with like OCI volumes. For those who haven't followed it, what basically it does in Kubernetes is it enables pods to define OCI images to be mounted as volumes into other pods. Why this is interesting is mostly, again, for AI workloads. So if you consider a situation where you have an application in a Docker image that knows how to run an AI model, but you don't want to package the actual business logic together with your model. So you're maybe building your model separately and then distributing it. Because we already have this infrastructure for OCI, it has become like a kind of a normal solution to package models in OCI artifacts. So what people used to do or still do is they run init containers and then share volumes and then copy the model over so that you can have 2 separate OCI artifacts. This is coming natively. It's a beta feature right now in 1.34. But the cool thing with it is Spegel works with this because it pulls images the same way that the kubelet runs normal containers. So what you can see now is like as this becomes adopted as like a normal solution, we're going to see more and more like AI models that are distributed this way with Spegel. And it's going to be interesting to see, like especially because it requires other projects like Kserve to actually integrate with these types of new features. So it's going to be really interesting to follow and see like how people are adopting this, because I think as OCI volumes become like standardized, we are going to see a larger shift from storing models in like S3 buckets and stuff like that to actually like packaging them more and more in OCI artifacts. As I talked about before, dynamic rate limiting is something, it's something that I haven't worked on before, so I'm pretty unfamiliar with the space. Really, the biggest challenge is that while you could set like a static number for like bandwidth and then set like, this is the amount of bandwidth you have and then divide that fairly, or set like a minimum amount of bandwidth, because it's an open source project and it deploys on so many different types of architectures, it becomes difficult to first of all, set a number. But so you end up having to like build a solution that dynamically tries to figure out what the bottleneck is and how quickly you can actually serve data to then implement some sort of rate limiting. So this is like one of those things that I'm really excited about, but yeah, hopefully will come to Spegel someday. Great, we're perfect on time. So community. I have been working on Spegel mostly on my own for the last 3.5 years. Currently, this is the adopters list. It is difficult to get companies to sign up and add themselves to the adopters list. So like what you see here is far from the reality of like companies that I talk to that use Spegel today in very large deployments. If you're a Spegel user at your company, please add yourself to the adopters list. It would be great, because mostly like you get a lot of new users come in and go like, great, project looks cool, but does it work? Does it scale to my needs? And it's like, it probably does, but I can't tell you who, sadly. Get involved. I run community meetings on Tuesdays at 5 CEST. So basically, Central European time. I try to keep it at 5, no matter if it's summertime or wintertime, mostly because it's easier that way. Add yourselves to the adopters list. I have a Slack channel in the Kubernetes Slack. Say hi. I'd love to have more people join. And I'm looking for people who want to do like case studies or tell me about their specific use cases of it. Just a quick shout out. I'm running a company called Reflektion around Spegel, trying to solve like larger enterprise problems that generally are difficult to do in the open source. So if this is something that you're facing today, also reach out. I'm here. I'll be here all week, most likely. So, and you can probably find me on Slack otherwise or in LinkedIn. So yeah, please reach out. Thank you very much.